Okay, great. So last class we talked a lot about points and curves. So now we're going to continue on to that. As I mentioned before, let's open up a curve and let's draw a simple curve here. And we're going to that curve. So one point, and we can reference that curve. So that curve is now from Rhino into Grasshopper. And we can start to manipulate it in Rhino, and it updates it in Grasshopper. We can also, there's a couple ways that we can start to add points to this curve. I believe I mentioned before, we have an evaluate curve, which is looking for, it's going to be using the domain of this curve. So, so we usually want to reparametricize. If you don't do that, I'll show you. Make this into a round. Oops. You notice that the curve domain is off. So it's strange because you're only going to 0 to 1. It's because we have to reparametricize this curve. So we have to reset the domain of it. So we right click over the C, we click reparametricize. And now that curve is able to go all the way through that. We can also do the point on curve, which is very similar, but it has a different interface to it. And we can slide that around as well. And you're going to notice Grasshopper will reference a lot of Rhino commands. So similar to what we were talking about before about curves, normals being flipped and surface normals being flipped, that still is applicable for Grasshopper. So there's even a flip curve. Which does exactly what it does. It does the exact same command as Rhino. It's looking for a curve to flip, and it flips the rotation. So if we need to loft something, we can do that. We also have a scale command. So what we can do is, when we have a scale component, there's a base geometry, which can be a line, a curve, a surface, or a B-rep, the center of the scaling, and the factor. So we could always scale this curve, and we can reference the center point of our evaluate curve. And let's grab a slider really quick. Let's just copy and paste this one. So Control C, Control V, and click that. So now we're just gonna unpreview this, and we're gonna hide this curve. But what we did is we created a relationship between the point on the curve and the center, the scaling, and how it's scaled on that. We can actually now, let's grab a subtraction. I'm just going to subtract it by 1. I'll put that into a factor. Oops. Not this. I want that. Notice now we have even more of a relationship where the scaling factor and the center point is based on our point on our curve. So again, it's another a relationship that we can create that helps generate some strange forms. We also start to have, we can also divide this curve up into different ways. So we could delete this really quick. Actually, divide curve, which we divide the curve into equal segments. So we can, and we need 12. Let's say we can divide this curve as much as we need to, and it outputs a point, the tangents, and the division points. So we can always have another curve. We're going to set this up. Just like, or we can set up, start to create some forms with this. And notice we're getting a little, some of the lines are getting crossed, or we could always flip this as well. So we could always flip it in Grasshopper, or we can flip it in Rhino. So the interesting thing is, you notice that this curve is divided into 49, and this one is divided into 28. So by this logic, it runs out, and so it just uses that last point to distribute that. And later on, we can start to explain to control that. And so if we don't want that to happen, how do we change that? Or how do we take every other point? There's a whole nother way we can start to look at how the data that starts to generate these lines is used. We also start to break points up as a shatter or curves up. So if we want to start to break up a point, and it's looking, so it's always looking for a curve to trim, a shatter, and the parameter to split at. So we're going to just copy this up. We notice that it's shattered twice into two planar curves. So that usually works when you have like more of a polyline, as if you had a lot of segments, you can break down that segments. With this, we really only have a simple, we have a pretty complex curve that we can do it. So it broke it up into two segments. But let's, but we can also start to create a little more relationships. As well, we can start to generate a graph. So there's some simple do is provide graph. So yeah, here, let's grab a grid. That's it. Let's do a square grid. So square grid is exactly what it's described. It's looking for a plane, which we're referencing our XY. We can always reference it as our ZX or our ZY. In this case, we're just going to reference our top view here. We'll draw that here. And then it's going to look for our grid sizes. Right now, our units are most likely millimeters. So we're going to change that to inches. And then it's looking for the extent of the grid, the number of bays it has in the X and Y direction. So what we can do is each segment is 1 inch. Let's set it to 4. And we can start to see, it's tough to read on this one, but we can start to see how it updates there. And there we go. And then right now it's generating 5 4-inch segments in the X and 5 segments in the Y. So we're going to, let's do 15. Let's make this a little bigger. Here, we're gonna copy, paste, right there. We can start to grow this thing and get pretty big too. We do it like a 45. So already when we create this grid, it tells us, hey, you have 2,025 cells and you have 2116 points. Now points are the intersections of these, and we can see those points by grabbing our point parameter, and we're going to plug that in, and there it is. There's all our points that are just that are referenced. So let's unpreview that. We don't need that right now, but it's very important that we got these point locations, because what we're going to do is we're going to put a circle at all those points. So just like as I mentioned before with these, how the logic of how the data flows through Grasshopper is very similar to matrices. So each one of these points, these are all the coordinates of all the points that are listed, all 2,000 of them. We're going to grab a circle, and we'll just grab the actual, like not the parameter, but the actual component circle, and it's looking for a point. So what it's going to do is it's going to take all 2,000 points and it's going to put them in this one point. So by plugging in that point, we're going to generate 2,000 circles, just like that. And part of the circle component is the radius. So right now it's just made all the 2,000 circles that are a radius of 1. And let's throw a slider in here. And we're going to make this max is 2. So now we're able to control all these circles. We want them touching right next to each other, or we can give them a little bit of air. We are now able to control all 2,000 circles with just one little slider. Well, what if we want a range of circles? So let's say it's like, I don't want all these circles to be the same. I want a variation. I want some of these circles to be small, and I want them to grade A out. And so they start small and they get big. Well, that's where we start to create relationships between the how to do that. And to produce that, what we're going to do is we need something that controls this. So what it's asking, what's the logic? How do we change these, scale these circles even or unevenly? So the first thing we're going to look to is, what's the influencer? What's the object that's going to change this? So in this scenario, we're just going to start with a point. All right, so this point is going to control these circles. So let's introduce that into Grasshopper. Okay, so we got our point into Grasshopper. We have to understand the relationship that this has. So, so these circles are going to change based off the distance relationship of this. So how are we going to get, how are we going to establish this relationship? So it's really important to understand, well, I need to know the location of this point, which I have. Let's see. Deconstruct. There we go. So that's our X value. Here's our Y value. So we have that information. That's good. We also have the location of all the centers of these points. Okay, so it's like, all right, so we have the two information. So what's the relationship? How are we going to bound these two things together? Well, it's the distance between them. So there's actually a distance component under our vectors. In fact, if we go right into our ruler component right there, and what does distance say? It says compute distance between 2 point coordinates. So that's great. So we can actually take those points, plug it into A. We also are going to take that point, plug it into B. All right, so I took that, and let's grab a pen. A lot there it is. It just measured all that. And let's visually display that. Let's grab a line tool. How do we know this is working right? Let's grab this point A. We're going to grab it into point B. There we go. So it takes all our 2,000 circles, generates a line that's based on that one point. And we can move that point around, and our circles, our lines will update. So that's good. All right, so the output of this is our relationship that we have. So what we could do, we're going to take our scale and we're going to plug in our geometry. So we want to scale our circles, and we're actually going to turn this up a little bit too. Help. That we don't need that. We don't need the lines anymore. Delete this as well. So all right, so we got our circles. We have our factor. This is our factor that can affect the scaling. So we're going to, the geometry that we want to scale, our circles, which goes into G. And we noticed suddenly, as soon as we did that, it shrunk all our circles to this point. Why that point? Because the default for scale is 0, 0, 0. So it scales it all the way right to that center point. And we're actually going to turn off, unpreview our grid and unpreview our circles. So yeah, it's like that is not necessarily what we want. We want to scale these based off that point. So we're going to take that our point, the center line of this grid, we're going to reference that right into our center. Okay, now it worked. It scaled everything uniformly using the center of these points. So, okay, we're almost there. But we want to plug in this distance because this distance is the factor that's going to control the scaling. So when we plug in D, we just kind of blew up. But one thing though that we noticed is that the values that D is outputting are huge. So it took our little circle and it multiplied it by a factor of 110, 121, 133. So it's like, okay, that's way too big for us. So there's a couple of ways we can do it. We could always divide it. We always divide that factor to get a smaller output. Oops, division. What we can do is we can always do the reciprocal of it. So put 1 into this. Okay, so we get some really small numbers if we do that. Let's take a look at that. Oh, wow, these are a little too small. It's almost non-existent. So there's a couple ways we can solve this. We can establish a bound. Let's see if this works. What that does is that sets the domain and range of that. Actually, might. There you go. I might just actually plug that right into there. So what that does is this for a second. So we plugged in our distance, and we used a bounds, which creates a numeric domain that encompasses the minimum and the maximum. So the smallest distance is 1.7 inches, and the largest is 215 inches. So so we have that, and we want to change that. We want to make sure that it produces a number that's more suitable for scaling. So we don't want anything really to be higher than 1, because or greater than 1, because that might blow it up. So we're going to, there's a command. We're going to construct our domain that we want to do. So there's a tool called construct domain, and it's looking for a start value and an end value. And so we don't want 0, because a scaling factor of 0 is 0, and that will create an error. So we're going to go something really small. We're just going to create a panel. We're going to say 0.01. And we're going to say our maximum is going to be 0.95. We're going to plug that into here, plug that into there. And so what does that make? That makes our domain of 0.01 to 0.95. So how do we get this domain to match that domain, we're going to use this command called remap. And what that does is it's going to, when it spits out these numbers, it's going to remap these numbers to a 0.1 to 0.95 relationship. So remap. What does remap looks like? It's looking for a value to remap, which is what our distance is, which our D is producing. A source domain, which is what our bounds is. And a target domain is what this is, our domain that we want to change. We're going to plug D, we're going to put right into V. I is our source domain. This other I is into our target domain. What's our output? It's our new output. So much more manageable than some of those numbers previously. So what happens to our scale factor when we use those numbers? It's a little easier. In fact, what we can do is we can actually bump up our circles so they're a little bigger. And now we created a relationship that the circles now change based off our point. We can also now start to, we can actually now create a, if we want these circles now to be surfaces now, for like, you know, these are some of the surfaces.
Hey, John.
Yeah.
Can you explain again how the remapping works?
Yeah.
Like, what is it actually doing?
So the remap is taking the domain of our distance.
Mm-hmm.
So here's our domain that is spitting out our distance. So that's our values. I'm just gonna reorganize this really quick.
Does remap only work for domain? It's just for domains?
No, well, it's yes. Well, yes and no. It can do domains, but it can also do single values. But it's really looking for, yeah. It can be values. It can just be a like a 0 to 1 or a 5 to 10. But what it's taking is it's taking whatever output, whatever number from your source domain, and it's converting it to fit this domain. So it's taking, if I wanted to remap, let's copy this over. If I wanted to remap we're going to do a quick, we're going to do a series. We're going to start at 0. Oops. Let's go up by 2. It's going to go up. Sorry, we just generated so, okay, we have a simple number of 0 through 2, 4, 6 that counts by 2. We're going to remap this 0 to 1. We want to remap this to fit into, instead of a 0 to 18, we want to remap those number outputs to fit between 0 and 1. So we'll get our bounds again. Bounds are, and so when we grab our panel tool, we should see that our bounds is 0 to 18. We're going to take our source domain, we're going to put our vertices, and what spits out is it converts those numbers to fit within 0 to 1. So it scales them down, it can scale them up, but it's a great tool when you have these large numbers and you just need to make things more manageable, or if you're later on, Remaps probably is a very powerful component. And later on, when we start working with optimizations and trying to find optimum schemes, Remap can be really important because sometimes we don't know a value that we don't like. Sometimes we're like, we have a maximum, but we don't really we don't know the maximum, but we just want to make sure it's within this certain number range. So we can take all those values and convert them into a number range that is more manageable, that we may understand. So in this scenario, we wanted our scaling factor to be not 0, but slightly more than 0, but not 1, slightly less than 1. So like that's why the 0.01 and 0.95 come in, because those, if it's 1, well, the scaling factor of 1 is itself, which could be fine if that's what you want. But if we get a scaling factor of 0, then it becomes an error. The output is 0. That's why we remapped it. It's also, we have more control over it. So that's if we did want 1. It's such a slight uptick from 0.05, but we could always change that, or if we want to change this to 0.5. It gives us a next extra level of control that we can work with. Some of these patterns that we produce here, they're pretty popular, especially when you're dealing with like screens or meshes, because you can easily take these, because the output of all this are curves, you can easily feed this into a laser cutter and get these laser cut, or a CNC machine, and you can have a pretty cool perforated mesh. You can also switch these design schemes really quickly, because what if I don't want a square grid? What if it's a triangular grid? Well, we can plug in the same stuff. We're gonna disable that. We're gonna plug in the points there. And now we just changed our script up, so now it fits onto a triangular grid. I might just turn this off. Or if we don't like a triangle, we can always go into let's try a radial. Yep. Right, or you can, so it's just a quick way we can rapidly produce design studies without doing this manually. And sometimes we might have to change this up a little bit. So we can start getting to that. And we can always mess around and look at different design schemes like that and change things around. Also, one thing that we can do is let's take the area of all these circles. Well, so there's an issue with what we just did in reality. So when we go and send this to a fabricator, they don't want to CNC these little holes, and you probably don't want to get these holes CNC because they are microscopic. It becomes more of a waste of the money, and especially with a CNC machine, how are you gonna, if you have a drill bit, how are you gonna drill that little hole? Becomes problematic. So we want to make sure to get rid of all these get rid of these points that are just that they're just going to drive up costs. They're not really doing anything. But to what scale should we, or to what extent should we get rid of them? So we're going to update this really quick. We're going to keep the triangle ones. Triangle ones are cool. We're going to scale this down a little bit so we were not overlapping. And I'm also, the command I used over here is called a boundary surface. A boundary surface, this only works on planar surfaces. And so what I mean planar is they are flat surfaces, or I believe it also works on perfectly vertical surfaces. But it generates a surface from curves. So what I can do is, since the output is the scale geometry, I can plug that G right into my boundary, and it generates a surface within that circle. So that's just a little easy way to visualize this. But yeah, the issue is some of these circles, they're just too small. So what we can do is we can grab an area, since that's the factor that we need to change. That's the information that is most important to eliminate these are the areas. So we'll reference that into scale. We'll put that in. And so remember, area always gives us the area of the geometry and the center point of the geometry. Since we don't really need the center point anymore, we're more concerned about the number. So we have panel. And there it is. So this tells us the area of the circle. So we're going to unpreview this because those points, so center points, get in the way of a lot of stuff. So it tells us the area of this, and we can see some of these areas are pretty small. So what we're going to do, we're going to balance again. We're going to grab our panel. So you may see this comes up. This is, I admit, probably the most difficult concept to grasp in visual programming, and that's data trees. Data trees are how the data is organized. So you may remember me doing a quick little command over here. It's a flatten. That reorganizes our data tree. In fact, if we're curious on what our data tree looks like, Okay. So let me bring up Google really quick. Maybe it might be better just showing a grasshopper. I thought they actually have a grasshopper data tree, but so think of as data as like a tree. So this area, or it's coming off one stem. So this one eye, actually, it's we have one input that's coming out of it, and when we start to, as this data splits off, it creates individual trees. That's the, let's see, fact. That's the diagram I'm looking for. So what that does is when we have one path of data coming in, that's essentially the trunk of the tree. But when the data can split off, and so if it's for example, if we have one surface and we break that surface up into 3 surfaces, that branches off into 3 different branches. And now we can manipulate this one surface differently from this surface. And we can also grab that surface different from here. So, and then when we manipulate that, that creates another branch, or it could create 2 other branches. And so it creates this branching effect where we can start to manipulate what happens here or the relationship that happens between these 2 branches. We can make data, there's ways that we can make data that's from one branch into hundreds of branches, or we can take all these little stems and we can flatten it and just make it into one stack of data. And so that's what happened in this scenario. You'll notice the word flatten. That's what happens when you essentially flatten the data into one trunk. So if we grab our panel tool and we look, we can see that it has, this is one branch, here's another branch, and here's another branch. And we know these are separate branches because there's an ID to that branch. So it's 0 semicolon 0 semicolon 1. And this is 0 0 0 and 0 0 2. So we can always, if we need to, there's tools that we can always extract these branches. So we can only manipulate the data in this one, or we can just isolate this branch and work on the data here, or we can remove branches, or we can say, you know what, let's reorganize this whole list and just make it one trunk. And that's exactly what we did with the flatten. Is if you right click over N, you get some of these commands. Flatten means we take it and we make it one trunk. Graft means we take all that data and we make it into stems. Simplify is just how we start to reorganize the the data structure, so it gets rid of some of these. You see a lot of these zeros and stuff. It reorganizes, it simplifies it, so it's only one data structure. I don't use it one too much, but or we can reverse the data. So it has, data always has a specific order that's generated. We can flip that data if we need to. So when we have this bounds, and so this is referencing our distance. So we have all this, and then when we flatten that, actually, click D, and we're going to flatten that. Oh, I might have just lost it. Hold on. I forgot to. Sometimes the dangers of a Grasshopper, because I think I might have made tons and tons of lines. Because I forgot to unflatten that. Bear with me for a second. Well, so right now what I did was it created there we go. There we go. There we go. Are you guys still there? Okay, cool. Launch this up again. So, no, we don't need that. We don't need it. So let's launch Grasshopper again. Great. So let's just do a quick series. Get this to 2. 10. So this should be just a very simple data tree structure. So it's just, everything is just one trunk. We know that. Because it's all straight order. There's no other ones of these. And we can see our branch is just one line. And even with, even Grasshopper tells you when it's just 2 lines like this, it means that it's just making one branch, or it's just one stem that's being generated. However, when we switch to graphed, we notice that the dash line changes because now it took the output and made it into all little branches instead of one trunk. So in the next assignment, we won't have too much of this. I don't think, if it is, it's pretty minor. But down the road, this is something that's going to be really important because it's going to help us organize some of this data, because you might be getting outputs that we want to change later on. Like if we need to call out certain items, or if we want to merge things or create start to manipulate this data, we can. Let's say let's take off graph. So let's just keep this as a simple stem. So if I want to let's just grab a quick
I have a quick question.
yeah.
Is it branching out because it's comparing to the original point, or what's causing it to spread out?
Let me back up really quick.
I understand, like, if it's in a series and it's going linearly, that makes sense. But then when they do graphed, I just don't know what that means.
So it's so when I graphed it, so actually let's multiply. Let's take this list and multiply it really quick. So I think we showed this. So we have I take that list, we're going to multiply it by 2. Our output, there it is, it takes our output. But when we graph this, it still does it, but now we can, we break it up into different, it's instead of reading this as, it reads this as a single list. So it reads this as one list that has 10 components into it. When we graphed it, it converts it into 10 lists with one component into it. So there's things that it behaves a little differently. In this case, when we multiply it, it still takes everything and multiplies it. But if let's see if what happens if we start to we isolate it. So let's list item. So list item takes an item from the list. So it takes this index, right? So that is our index for the list. So we're going to take this guy, and we want index 0. So it's usually it's just throw a 0 right on there. So with this list, that's actually we'll make it 1. We'll make it 6. So with this, we should be able to spit out $12, because it's taking the index of 6 from this list, which is 12, and it spits out 12. When we graph this, we notice that when it takes 6, well, there's no 6 to take from, so it takes the full list. Because it's saying, wait a second, there's no index that's 6. There's only index 0. So that's where sometimes, like when grafting doesn't work, doesn't make sense to use this, because you have all these indexes that are the same. So that's where some of the order does matter on how we want to calculate these things. I believe if we did, let's do this as get rid of that. We did a mass addition. I should say 90. But if we graph this, it's saying, well, pulled up, there's the mass addition only works on, it will take the lists and adds them all up. But there's 10 lists with only one index in it. So it's saying, yeah, I'll add all this up, but 0 plus nothing is 0, 2 plus nothing is 2. So my output will be that. So if I have 2 series, let's say, and we're going to add them up, it takes those 2 lists and boom, adds them up to 180. So the output is, it takes those, adds them all up. But if we graphed them, well, actually, ironically, when you graphed it, let me grab a panel here and show you. So when we graphed it, we have our 10 lists with 1 index each. But the non-graphed one is 1 list with 10 indexes. So what it would do is it's saying, okay, list 0, 0, all these values are going to be added up to list 0, 0. And what's that equal? That equals 90. But then what are the other indexes that add up? Well, it's 0. Well, I'm sorry, it adds up all this, throws it onto a graph, or throws it on a list, and then it takes this list and adds it to that. So you have so what it essentially did was it just took another branch and stuck it on this. So if we graph both of these, well, then it knows, okay, I'm going to take 0 and 0, add them up, that's 0. I'm going to take 2 and 2, that'd be 4. And so it's comparing the 10 lists with the 10 lists and adding them together. We can also start to we can also call out certain values out of the data. So let's do a call index. So I used a list index or list item, which calls out specific items in the index. I can also remove specific items from an index. So I can always put this in and which index I want to remove. Let's remove 5. And the output of this should be the same, but I just removed 5, 0, 2, 4, 6, there, 10. So we're missing our 10. We also we can also start to introduce patterns into this. So what if I just wanted to get every other item out of this list? I can do a call pattern. What is call patterns looking for? It's looking for a list to call and a pattern. And the pattern, when we see that icon, that circle that has that's half filled in, half empty, that's a Boolean statement. So a Boolean statement is different from Boolean in Rhino. So in Rhino, when you think of Boolean is, oh, I'm editing geometry. I'm removing this geometry, or I'm Boolean union these. It's a completely different meaning for programming. Boolean statements are true-false statements. So the default of this is false, false, true, true. So it's going to remove 2, keep 2, remove 2, keep 2. So just for example, we'll put that in, put that out, and so it will remove 2 of the indexes, keep 2, remove 2 of them, keep 2. We can always change this too. We could always type it in, or we can go into Boolean or go into our values, and we can always do a Boolean toggle. I'll say toggle here. We're going to control copy paste. So we can set 1 true, 1 false. We can plug that in and plug this one in. We'll plug that right into there. And there it is. We called out, we removed every other list, every other item on our list. We can also start getting into some statements to like, if things are greater than or less than. So we could always say, yeah, let's do that. Yeah. So if we want, actually, let's go back to our circle one. That was let's grab our vector, our triangles. This time, instead of a point, we're gonna change these. We're gonna change this these circles based off a curve now. Maybe a point which just wasn't doing it. And you know, yeah, I think it's there we go. Let's reference a curve. Great. So there's our curve. Works there. I'm going to divide this curve up. I'm going to divide it by a lot. We're going to divide it by maybe 0.5. I think this is the one I want. Closest point. So curve closest point. So it runs the exact same logic of what we just did before, but instead of taking 1 point, it's going to take these points that are along that curve and it's going to grab the distance. So there's a command called curve closest point, which is in the curve. So actually, let's go there. Curve in the analysis. These are a lot of great tools that just, if we need to create perpendicular frames, or if we need to close a curve or extract points from a curve, anything that a curve generates, so we can grab dimensions from a curve, we can grab points that define the curve, we can grab frames that are perpendicular from a curve. There's a lot of great tools in this analysis drop down. But one of the great ones is this curve closest point. So what it's looking for is it's taking points to project onto curve. We're going to take the points from R. Oh, and we don't need the divide. And then we need our curve. And it's going to take the points that are closest to this curve, is essentially what we did with the line. It's going to take these points and it's going to project them onto this curve. Sorry, I didn't need to define it. This is what generates it for me. And the output are the points on the curve that are closest to the base, the parameters of curve, the domain of the closest, and the distance of our curve. So let's grab our bounds really quick. See what this is. There it is. So that is probably each point. So we're actually going to flatten this because we don't need it in graphs. We don't want each and every little. So let me go back really quick. So what this just did was it took the point, projected onto the curve, spat out a distance, made a branch of data, then took the next one, read the distance, projected the point, made another branch of data. And so what it's doing is it's creating a domain that defines this point to the point to the curve, and then another domain that point to this, and to this. So we have all these, we have 2,000 individual domains. We don't need 2,000 individual domains. We want to look at the entirety of the domain, from the point that's closest to this curve to the point that's furthest away from that curve. We want to know the full extent. So that's why we flatten it. And that gives us our overall domain that we want to use. And we're going to grab our domain again. Construct domain. Do 0. Actually, not 0. We're going to do 0.01. Do this as maybe we'll just do it 1 for now. And we'll go back to our remap. Remap numbers. We'll plug in our distance to here, our source domain, and our target domain. And I think we're good with that. Yeah, I don't think we need to flatten that one. And we're going to grab our scale. What are we scaling? We're going to scale our circles to our center point and our factor. Turn this off. On preview, on preview. Preview. And there we have it. If we need to grow these circles a little bit more, can. Clear that into, yeah, it's just something like that. Make it into down the integers. So we can start to get like this. We always define these as a little smaller if we need to. So we can, so the nice thing with this domain is we can see how much it influences the scaling. We can also that maybe we'll so we can always influence that. So maybe it doesn't have, the curve has very little influence to it, or maybe it has a lot of influence. So going back to, I was originally looking into is when we fabricate this, these areas. Let's grab our area, turn that off. Area. We'll just take a look at what we're doing. Flatness. Okay. So our largest area of our circle is 8.2 square inches, and our smallest one is 0.04 square inches. That is pretty small. So what we're going to do is we're going to get a evaluate. And what evaluation is it's looking for an expression and the X factor that goes in, or a variable that goes into it. And it can be a variable X and Y, and we can actually add more if we need to. In this case, we're just going to make a really simple one. If we're going to grab our panel tool, we're going to say if 0, 4, or less than, we're going to say 5, less. So let's get rid of everything that's one square inch. So that's our expression. So it's red because it's saying I'm missing a variable. So we're going to plug in our areas. And the output gives us, now it takes this whole list. So it takes how many, it takes our 2,000 points, and it compares them to areas that are less than 1 square inch, and it creates a true false statement out of them. So what we can do now that we have that, we can grab our dispatch. What does dispatch do? It takes a list and it breaks it up into true false statements. So if we take a list and if we take our scale geometry, we're gonna plug that into here, which is essentially the same list as the area, and it's going to compare it to the true false list, and it's going to break it up into two different lists based off it. So all the trues will go one way, all the falses will go the other way. So let's grab our curves. There's all the curves here. Here's all the curves. So you see the ones that are highlighted in green, those are all the curves that are greater than 1. These are all the curves that are less than 1. So we'll turn those off. Let's turn that off. Okay, so that's a little harsh. You know, we still like that gradation to it. We got rid of a lot of it. So let's tone this down a little bit. Let's say 0.0 8. And it updates, and it's like, okay, now we're starting to get our gradation back. That what we like. And maybe we push it. Maybe it's 0.5. Yeah, maybe that we're losing it back. So maybe it's 0.1. Okay, so all right. So now we're starting to get rid of. We don't want to get rid of all of the gradation, but we just want to control it and manage it. So this becomes a lot easier for someone to CNC or laser cut. Now they don't have to get rid of all these little holes. Another application that we've used these on have been like stair rails, like for code, like stair rail or guardrails. You know, you can't have a circle that's greater than 4 inches. So we want this great pattern, but we don't want anything that's greater than 4 inches. So we start to, so that this is just another way we can control these circles so we don't exceed that 4 inch, or we don't exceed those 4 inches. So but it's just another level of control. It helps with fabrication. So now it's, like I said, this is pretty easy to cut. You don't have all these curves. And so now we can just take this guy. We'll actually just hide this, turn that off, preview, and let's make a layer. Can just bake these right on, and we'll group them since there's so many of them. And there it is. So now we have our little circles. Now, also, you know, when you laser cut these and you want some material in between these, you probably don't want them overlapping. So just another level of control, but that we can further manipulate. So, so we can also start to, so that was our 2D example. So we can also start to generate 3D examples. So let's just do a quick save as on this. Cool. So the next example is, let's say we have our, let's say we have a our buildable area. And that's going to be like 5 feet. That's a little too much. Let's do 75. So let's say we got our, this is our buildable area, and let's bring this curve. Set point. So we have our, let's change this into our perspective view too. So we have our rectangle, and we want to start to make a little tower out of this. So what we're going to do is we're going to bring it into a series. We're going to move this up, actually. Let's move this. When we move it, we're going to move it up. Let's change our direction. It might be easier to use. Just screw up my. Nope, we're good. Okay. So we're gonna move this Z, and let's say there is a this is a 100-foot tower. So what we have, remember with move is you know, we can reference the geometry that the move is and the output of the move. So essentially we have two curves, right? Because we have our curve A and our curve A prime. Still curve A, but it's just moved up. But we could always, just like with Rhino, loft these. And very similar to Rhino, the order we input this into loft matters. So if we want to start with the bottom up, so we plug A in, and then we want to hold shift, we get our little plus key and drag prime in, and there's our box. That's our surface that's defined by these two curves. We can always rotate this top curve now if we want to. Let's say if we want to further manipulate this, we could, let's do rotate 3D. So what rotate 3D is looking for is it's looking for our, oh yeah, and it's also located under transformation. A lot of our like move, rotate, scale, mirror, all that's under the transformation tab. So it's and if we want morph or twist things or scale them, all that stuff is in the transform tab. So rotate 3D is looking for our base geometry. It's also looking for our rotation angle that's in radians, our center of rotation, and our axes of rotation, which our axes rotation, we won't have to worry about that because we're gonna just rotate it this way in it's essentially referencing Z, but if we need to rotate it in a different direction, we can, but it's essentially just, if we're in top view, it's rotating it along the Z axis. But let's shift this over. So let's rotate that top curve. And there's a couple tricks that we can do. So we're going to drag and drop, drag, connect that. Now the default is a half times pi, which is 90 degrees. I am not a fan of radians. I prefer degrees. So this is a newer feature that they had, and thank gosh they did it, because it makes life a lot simpler. But you can actually right click over the A, and you can say degrees. What that does is it converts the output into degrees. So now when it's taking half a pi, it's actually taking half a pi, the output, and converting it and giving it a degree instead of a radian. So, which is a lot nicer, because if we want to do 90, now it's a little easier if we can do 45. But notice that the center is at 0, 0, 0. The rotation is. We don't really want the center to be there. We want the center to be at the center of this, because we want this pivot. Now we could always loft it if we really like that form, and it generates something like this. I'll preview this, and we could always do something like that. But I want something. I want to loft this base. I want to rotate this geometry based off the center. So we're going to get an area, because that's how we find the center of a curve. So notice when we grab our area, there's our center. It also spits out the area of the geometry. We're going to unpreview that, and we're going to drag our center right into our C of this. And so we know it's that circle, that little point went away, because now it's this. And now it rotates based off the center. We're gonna so now when we rotate it, it's going to be based off the center. We also can cap this. The great thing about Grasshopper is a lot of the times, and I wouldn't say all the time, but a lot of geometry it produces, it's watertight now. So if later on when we want to 3D print this, which the geometry that we are going to be producing in assignment 2B, we will be 3D printing. So it's key that when we cap it, we put a panel, it says close BREP, which is really important, that word closed. But let's say we have a whole bunch of floors. Say we want to design this tower, and we want to divide it, we want to rotate each floor a certain degree and have it twist all the way up. So what we can do is, when we have this move, you know, it's moving up 100. We want to generate a lot of floors. So what it's doing is it's taking one variable, and it's adding one thing, pretty much comparing it to one variable. We want it to we want to move multiple floors that are the same footprint of this. So instead of inputting one number, we want to input multiple numbers. So the best tool for that is our series component, because this is how we are going to generate a series of numbers. We're going to start at, we're actually going to start at 18. 18 is a pretty healthy amount. And why we start at 18 is a lot of times for retail, for architecture, the retail space, which is on the lower floor, wants more ceiling height. Because when higher ceiling, right, studies have shown that retails are more successful. Also, they're more flexible to do their things if it wants to be a restaurant or a coffee shop. So we're going to start off 18. And then we want the number of the increments it goes at. So for office, it's typically 14 feet floor to floor. For residential, it can range from 10 to 11. In this case, or sometimes 9, as low as 9. But in this case, we'll go with 11. And so we'll crank that in. And how many floors do we want this tower? Well, we want this pretty, the developer wants to make this a pretty, this is a pretty big development. So we're gonna make it 100 stories. So, and if we look at our panel, it spits out 18 and it goes up in 14-foot increments. So we're going to take that and we're going to spit that into our move. How we just generated this curve 100 times, starting at 18 and then increments of 14. So let's see now. Let's actually disconnect this for a second. Move this aside. Move that aside. So we could just take this curve and take that curve and this curve. And you notice that nothing happens. Why did nothing happen? Let's see. Take our panel. It says it's reference, so there's one curve, it's referenced there. What's going on with this one? So there's a whole bunch of lists. So that's strange. So you're like, okay, why is that not working? Because it's reading, okay, how am I gonna reference this loft and generate a surface with this one with all these? The order of which it's trying to generate it's having a hard time figuring out, so that's why it didn't generate anything. Oh wait, I lied. Oh yeah, see, it didn't reference this guy because it took all these and created a surface, but it skipped this one because it can't create that surface. It doesn't know what to do with this. So this is where we want to flatten it. When we flatten it, and of course, the order of this matters when we put it in. It now creates a nice clean list. So now we see reference polyline curve and then all the generated curves that we just made. So that's important. So that's why we had to flatten that. So it picked up that last curve because it was on a different branch. So we have our tower, but we want it to twist. We want each floor to twist a little bit. So it's the logic that we do it. It's exactly the same way we did with the first one. We're going to get our curves. We're going to keep this bottom one the same. We're only going to influence these. We're going to grab the area. We need the center of that. So we'll keep our area. And we're going to plug A right into G. preview. And we're going to disconnect all these. We're going to preview this. That there. It's here. It's like, wait a second. Only that bottom one changed, not all these. It's because we're only taking all these curves and we're only rotating. We're rotating this chunk 44 degrees while this is at 0 degrees. So we want to generate multiple different angles for each one of these floors. So it's the same logic for the move. So just like with the move, we just had one input. With this, we need several inputs to go into that angle, that degrees. So we're just going to take this, I'm just going to copy it over really quick. Actually, I'm going to delete this one. So we need 100 angles to have this thing evenly twist all the way up. So we'll keep our starting at 0. And we can control the increments of how it rotates up. So maybe we'll just start at 4. So every floor is going to rotate 4 degrees. And since we used since we generated 100 floors for here, we're going to use that same 100 to plug right into C. And we're going to take that series and we're going to plug it right into A. And then we notice, wow, every floor now rotates 4 degrees and we get this nice organic flow to it. What if we don't want 4 degrees? What if we want it a little smaller? We can make it like that. We actually change this up, edit, actually make it like that. And we probably don't want 100 degrees each floor, so we'll switch it to 10 degrees at the highest. So we can start to see how and we can really crank that up and it can get really spirally if we want to. We can ease it back. And the nice thing, because this 100 is based off the number of floors that we move, we can also influence that. So if this thing is too tall, we can slowly change that up. So let's so if I have say I have an elevator core that goes up. Now the elevator cord should not twist with this, but elevator cord should go all the way up with it. We can have this and what's that? One. We're actually going to area this. So we got our center point. Good. We're going to move this guy the same as before. So we got all the little floors here. That's cool. So what if we want to get some actual like floor plans on this? And they're not going to be really highly detailed, but at least they can be some diagrammatic floor plans. we're going to, we want to lay these out nice and flat, just like a floor plan. And we're also going to do color these really quick. So we're going to do a boundary surface on this. We're going to do a preview, custom preview. We're just going to change the color of it really quick. We can go into parameters. It's actually oh, my bad, display, previews. Oh, sorry, color. Should be a color swatch for somewhere. Let's just go color swatch. Where is that? Okay, oh, I was right. First parameters, color swatch. So what we can do is we can actually double click on our swatch and we can actually define a color to color this. We actually then, let's do the same thing for these guys. In fact, instead of lofting it, the loft is great for the form. We're actually going to unpreview that. And we're going to get we want this, do a boundary surface. That, and we'll get a preview. White, but we'll get it. There we go, some orange or something. So let's grab the area of this guy really quick because we need the center point. We're going to unpreview this. And just to help make things a little clearer, we're just going to plug a point parameter in there so we know what we're looking for. And we're going to do the same thing for this. Center, go. Turn this off. And we want to lay these out evenly so we can read them. So we're going to use a command called an SDL line. It's a different, it's creating a line, but it's creating it in a different way than the line that we're used to. We're used to a line that is, okay, a line is defined by 2 points. Well, in this line, SDL line is defined by a start point, a direction, and a magnitude or a length. So in this case, we're going to just, the default for it is, actually, I don't think we're just gonna set a default, set point. We're just gonna say 0, 0, click enter. There it is. So our point starts at the origin, our direction. Our direction, we're gonna go in the X direction, just for example. And we're going to magnitude of, we want something really big. So we'll go over there. We're going to, that might be too big, but something along those lines. We're going to divide it. And how many times are we going to divide it? We're going to divide it. How many levels? There's 69. So we're going to divide it 69 times. Might actually have to make this a little longer. So that gives us our point. We're going to make this point. And now these points are going to be pretty important because we're going to use a tool called Orient. What Orient does is it takes an object and it references it at one point, and then it transforms it to a different point. So essentially, okay, this point is here. It's this geometry is here. It's defined by this point, and now we're going to move this geometry to this point instead. So that's why it's really important why we have our center of our floor and the center of our elevator shaft, because we're going to translate those onto these points. So we're going to take our surface, we're going to put that into the geometry. So it's asking for base geometry, initial plane, and our final plane. So our our floors, the original location of them, which is the area, so we'll put that right into A. And notice it, and then we're going to move them along this point B. And so there's all our floors. And we actually can see how they rotate around. We're also going to do the same thing for our elevator shafts. Going to boundary, take our initial, and we want it on this one. And there's our elevator shaft. And we can study these a little closer, because now you can start to see, okay, everything's fine here, this works, this looks good. But as the tower turns, you're like, oh man, this might be I might get a pinch point here, and I can start to design, and I have a little extra level of analysis I can do. It's also just generate 69 diagrammatic plans that you can study. This is also really important for when you do stuff that for digital fabrication, when you want to want to lay out things to get things CNC cut or laser cut, but it's all these different forms that are complex. Well, I can just break it up into pieces and then orientate them along a curve, and now I have a nice flat object that I can either send to the laser cutter or CNC machine to cut.
I know we're after time, but will we be able to go over the assignment for
Yes.
next week?
Yep. That is my next thing.
Okay.
So that leads us directly into our next assignment, which is a continuation of assignment A. I believe it's already posted.
It's posted, but we can't. I can't access it. I don't know if anybody else has tried.
Okay.
Can't
I'll,
open it yet.
Okay, I'll go.
Yeah, it
but
says
after,
not authorized.
Okay, after this, I'll look into it. Maybe I actually put a time limit on it. But yeah, so we're following this example of, we have that developer who's looking into one of the sites. Now we're going to take that site that you picked from assignment 2A, and now we're going to start generating some massing out of it. And so in this assignment, we're going to generate 5 massing studies, and we're going to generate these massing studies based off some parameters. So on the first floor, we'll have a 20-foot tall finished floor, and then each floor after that is going to be a 14-foot floor to floor, just like I've showed you. We're also when we generate these massing studies, we need at least 1 perspective view of each massing study, so 5 perspective views, and you're going to generate colored diagrammatic floor plans for each massing option. So if you have, if you happen to have a design that's 100 stories, you're going to be generating 500 diagrammatic floor plans. And they're all going to, and the way it's laid out, it's going to be, you'll be able to color all of them as well. Note that you are also going to be looking at the gross square footage of the design, the rentable square footage, and the total building efficiency. Now, those are essentially, to get a building efficiency, it's taking the rentable square footage and dividing it by the gross square footage. It's that easy. It's just time, and then times it by 100. So when you design this and when you start laying out the massing, your efficiency for this shouldn't fall below 85%. I don't think anyone's will, but just keep that in mind. And that's part of that's something in development that architects have to follow. Efficiency is something, if there's a building that's not very efficient, then the developer can't make a whole lot of money out of it. It's also not a very good building. And what I mean by good, it really actually depends on the building type too, because some buildings are less efficient than others. So you're going to be referencing the assignment to be Grasshopper script. What I recommend is using your Grasshopper script from assignment A and your Rhino file from assignment A. Reference those, and you can pretty much copy and paste Grasshopper assignment to be into there. And what I mean by that is, if we open up simulation and fabrication, oops. We can open up this. I can essentially take this, copy it, Control C. I can do a Control Tab, and it tabs over to my next script, and Control V, and pastes it right in there. So very similar to the assignment from before. I'm going to give you all the Grasshopper components. It is your job to connect these in the correct order to generate the rentable square footage, the gross square footage, the efficiency, colored floor plans, and the massing diagrams. And I need to see 5 design options. And when I mean by design option is, if I look into this design, for example, and it's this twisting tower. Where's my rotate? Let me find my rotation of the floors. There we go. You know, that could be one design option. I'll find a view, do it, follow the graphic standards, snap a picture of that. Okay, that's view option 1. Let's then switch to the top view. You might have to do several view captures to capture all these floor plans onto one sheet, but capture all those. Okay, I like that. Study. Also capture your Grasshopper script for that design. And then next one is, okay, I like that design. That's another design option. Do the same thing. I like that. That's a design option. So it's quick iterations. So it quickly produces your floor plans and different design schemes and different efficiencies. In this script, we're in the next assignment, you're actually going to take this form and take it a step further, where it's not only rotating, but it's also going to be tapering too. So it's going to be, so that's why your floor plans won't always be the same. And your gross square footage and your rentable square footage won't always be the same, because the top part's going to be getting smaller, and that's going to influence quite a bit. So again, I'm looking for similar things from previous: precision, scale, accuracy. Model composition is more of Grasshopper script composition. Is it put together correctly? Are the things in the right order? Organization and hierarchy mostly is this thing organized and it has a logical sense on it. It's not, these components are just everywhere. It should be neatly organized. And of course, if these tools are connected correctly and if they are generating the correct information. So February 11th, which would be next week. And like I said, just you could bake your perspectives or bake your massing models and put a display on them, or you can just use the Grasshopper default as one option, and then this would be an option. And these are the examples of how the floor plan should be laid out. It doesn't have to be all laid out as, you know, X amount of floor plans along a row or column, but just have it fit in the best way you can on the sheet. So let me know if you have any questions or concerns. One last thing, I know I'm going over, but one last thing I brought up was the rounding. With your areas, we get our panel tool. Oh, of course, it's a, let me change this really quick. So now we get this weird number. We can always round this. So it rounds the number to the nearest integer. Just do that, we'll plug it into there. And there it is, it drops it, it rounds it. So if you need something a little cleaner. I do have that component in next in the assignment 2B. I also have a merge as well, and merge is not, it's essentially merging lists together. You guys don't have to specific, like it's not super complicated. Is essentially just taking that list and that list and spitting out one big list that combines them all. And that's all, that's the extent of it. It's not super complex in this instance that I'm using it. And I also have a cap, which I believe which I did show you before, which was how it turns into a closed BR. As I said before, this next assignment, the assignment after this one, we will be 3D printing these design options, and so just a heads up, do make sure that things are closed off. So, but yeah. But is there any other questions? Okay, great. Well, don't forget to submit assignment 2A tonight. I should be getting the first assignment to you guys shortly, and I'll double check on assignment 2B, make sure it's unlocked for you guys. All right, great. Thanks, everyone. Sorry I went over.
That's all right.
Great.
Thanks.
Thanks a lot.
Thanks.
Have a good one.
You too.